Hello and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video we're going to go through section 6.2, how to find volumes. The best way really to think about volumes is to consider volumes that you are already familiar with, that being the volumes of cylinders and of rectangular prisms. The volume of a cylinder, if I draw it horizontally here, the volume of a cylinder, where a cylinder looks something like this. I'm not the best artist, but I try. What you try to do is you try to find the area of the base. So the area of this base right here. The area of the base, since this is a circle, we represent as pi times r squared. Then when you have the area of that base, what you do is you multiply it by the height of this cylinder. That's how you find the volume of a cylinder. Same applies if you have a rectangular prism. Rectangular prism looking something like this with the background there. If you try to find the area of a rectangular prism, what you're trying to do is you're trying to find the area of one slice of it, which we'll call a cross section. You're going to try to find the area of one slice of this. This would probably be represented as length times width. And then when you find that area, which is just length times width, you would find the volume by multiplying that cross section by the height of it, which again we'd represent by h. That is generally what we're going to do to try to find the volume of any given solid here. We're going to try to find some given cross section and then multiply it by its height. However, most cross sections we deal with are not going to be very nice. Let's say it looks something like that. Yeah. Something that kind of looks like a cylinder, but more looks like a warped cylinder of some extent. When I make a cross section, whether I make the cross section at the end here, or if I make the cross section in the middle, just to represent it, this cross section that I have is going to have various radii. It's not going to have the same radius. When it's here, it's pretty thin, but when I make that cross section over here, it's pretty thick, and that radius is all being defined by the curve of this. Therefore, we're going to apply a similar concept as we did before. What we're going to try to do is find a formula that represents the area of this cross section, and then what we're going to do is integrate that along this distance, along that height. That's overall what we're going to try to do. It's also going to work in the way of Riemann sums, where we make maybe thick slices of this. Maybe I make some kind of a disk here, and I make a disk here, and I make another disk here, something like that. Then I'm going to try to minimize how wide each of those disks are, which leads us to a formula that looks a lot like it did for just the definition of an integral. Here, we're taking the area of each of these slices that we create, multiplying by how wide they are, and overall we're trying to decrease the width of this or increase how many of these intervals we have. So that means that we can find the volume of anything by looking at the integral of the area of a cross section. And if you notice, the cross sections that we created in that previous example were all circles. If I were to make those as thin as possible, they generally just become the area of a circle, which we know as pi r squared. Therefore, we can solve these by finding the area of cross-section as pi times r squared, where r is the radius, draw it in blue, is the radius of that curve at any point. And we can integrate on that. Now, there are other methods of doing this, but this is the method we'll talk about first in 6.2, called the method of disks. This is where we use the formula a equals pi r squared, which is what I was talking about, where the radius r is the equation that represents the slice perpendicular to the axis in question. Now, what that means is that if I have, say, a curve like this, well, when I'm trying to find a volume of it, I would first find this area, and then I'd determine what I'm trying to rotate it around. If I'm trying to rotate it around the x-axis, then that means that r is going to be in terms of x. if I'm rotating around the y-axis, that means r is going to be in terms of y. So it's going to agree. As it says here, so if you're rotating around the x-axis, then your radius should be in the form of r equals f of x. If you're rotating around the y, r should be in terms of y. Therefore, you get the following general equation for the method of disks. You get the volume from a to b, a of x, d of x, where a and b is the bounds of integration. And you can have a to be pi r squared, which pi is a constant, so you can pull it out in front of the integral, and you have pi times the integral a from a to b of r squared dx. Now, you can also do this if you have a difference of curves. In this case, this would sometimes be called the method of washers, although the method of washers is more or less just a subsection of the method of disks. A washer is basically, if you think about it horizontally, this is where you would have a curve like this, and then another outside curve. And if I make that three-dimensional in some way, something like that, then what I'm trying to do, if I consider an axis going through it, I'm trying to find the area of this by considering what the far area is, or the furthest curve is, and then I'm going to subtract away the area of the innermost curve. If I can do that, then I'll find the area of the washer itself, this outside region. I basically just be cutting out the middle disk. So it should link up to what we were just talking about in 6.1. And those formulas generally look like this. Again, this is generally for thinking about it in mostly quadrant 1. So I have radius of the top minus radius of the bottom, or radius of the left minus radius of the right. So set up in the same way that I did with those in 6.1. Generally, they're just the furthest one minus the closest one, which is also what I talk about down here. Now, one last thing before we get into some examples. If you are rotating around a different axis, you will need to account for that when constructing your radii. So that means each individual equation, if you're rotating around a different axis, you're going to have to subtract things appropriately inside of the radius. So that means inside of that value that you square, or that you take to an exponent of 2. We'll see a couple examples of that, so you'll see what I mean in just a moment. For now, let's dive into those examples. I have 6 different examples to show you here that all go into different concepts of this. First, we have this example that's also coming from the book, so if you want to see it done again in the textbook, you may. It's on page 439 to 440. It starts on 439, the rest is on 440. And we're trying to show the volume of a sphere of radius r is v equals 4/3 pi r cubed. Now that might be a formula that you're familiar with, and what we're going to try to show is that that is true. Well, let's try to draw a picture of a sphere. Now again, I'm not the best at this. So circle like so. And then if I'm trying to consider a sphere, it comes out like this, and then goes in. So something like that. Again, I'm not the best artist. But what we can really try to do is find this volume by rotating around one of the axes. Now, it's up to us which axis we want to do. I think the book does around the x-axis, and that's the one I want to do as well, which generally means that I want to find a slice like this, and I want to rotate that around this axis. Well, in order to do that, what I'm really considering is just the top of this. So if I redraw this, what I'm really just considering is the top of the circle. And then I'm going to take that slice, and I'm going to rotate that around. That's what's going to create my sphere. Well, in order to do this, I noticed that these are disks, and I'm going to be able to use the method of disks, which is pi r squared. But I need to know what this, what the radius is, or what the equation of this line is. It says the radius is r, which means it goes to r, it goes to negative r technically. And we need to know the equation of the line. Well, we do know that. We know the equation of a circle is x squared plus y squared equals r. And if you notice I'm rotating around the x-axis, that means I want to get this in terms of x. So I want to move x to the other side and solve for y. So this can be represented as y equals the square root of this should be r squared minus x squared. So that's the equation I'll use. Now, again, I said I can also do this by rotating around the y-axis. It would work exactly the same. Then I would just use the formula x equals square root of r squared minus y squared and rotate that around horizontally. That works too. You have a couple different options here. I just want to go with x-axis because that's the one I'm more familiar with. And you as well. So we can find the volume, which is the integral from a to b, which is going to be negative r to r. And then we have pi times r squared, or I'll say radius squared, dx. In this case, my radius is that formula, is the square root of r squared minus x squared, dx. That is the radius of the slice that I am creating. Remember, the radius in the equation pi r squared is considering this slice that we created right here and what the radius of that is. This works really nicely because that's an ugly square root, but it's being squared. So if I pull out pi, I get negative r to r of r squared minus x squared dx. And then I can integrate on that. That will give me pi times r squared. R squared is a constant, so that's really r squared x minus x squared is not a constant, that's a variable, so that's 1/3 x cubed from negative r to r. Move up here so I have a little more room. If I plug in these appropriately, I'll have pi times, if I plug in r, I get r cubed, because that's r squared times r. So r cubed minus 1/3 times r cubed. And then if I plug in negative r, I get minus the quantity r squared times negative r is negative r cubed. Negative r into x cubed is negative r cubed times a negative 1 will give me plus 1/3 r cubed. So overall, we get r cubed plus another r cubed, so that's 2r cubed. And then we get negative 1/3 r cubed minus another negative 1/3 r cubed, so that's minus 2/3 r cubed. And if you do 2 minus 2/3, that does give you 4/3. So we do get 4/3 pi r cubed as our answer there. All right, so that's showing that we can get the volume of a sphere using the process of integration. So if you wondered where that formula came from, why it is kind of similar to pi r squared but is different, this is why. Okay, let's do another one. These next two should be a little more basic. First, rotate y equals x cubed plus 2 around the x-axis from 0 to 2. Now again, first thing we want to do is graph this. X cubed plus 2, that's a cubic function that's vertical shifted up 2, and it goes from 0 to 2. So we have from 0 to 2, this is shifted up vertically 2, and so that looks like a standard cubic function. If I even want to find where it hits the y-axis, or where if I plug in 2, I get 8 plus 2, so it goes up to about 10, if I really want to know. But this region right here is what I'm going to rotate around the x-axis. Since I'm rotating around the x-axis, I want to keep it in terms of x, so I don't need to do anything to the function. I can solve for this pretty nicely. V equals pi from 0 to 2 of r squared, where r is x cubed plus 2 squared dx. All right, now we can't just solve this right now. We do need to apply that exponent to this polynomial to get a longer polynomial. What we'll get is x cubed times x cubed, which is x to the 6th, plus x cubed times 2 multiplied twice, so that's 4x cubed, and then 2 times 2 is another 4 dx. And then we can apply my integral. So that'll be pi times 1/7 x to the 7 plus that'll be x to the 4th divided by 4, so that's just x to the 4th plus 4x from 0 to 2. Okay, well, on the bright side, one of the bounds of integration is 0. That means when I plug in 0 into all these terms, all of which would include a variable, they're all going to cancel out. So I do not need to even consider plugging in 0. I will need to consider plugging in 0 if it had different things, like if it had e to the x in it. But in this case, this is just a polynomial, all of which have terms of x's. So if I plug in 0, they all will cancel. So just plugging in 2, I get 2 to the 7th, which is 128 divided by 7. Should be 2 to the 7th. Yeah, 128. Just making sure. 2 to the 4th, that gives me 16. And then 4 times 2 gives me 8. So if I want to simplify that, 128 over 7, 16 plus 8 is 24, and 24 times 7 is 168 divided by 7. And if I add 168 plus 128, I get 296. So pi times 290, I put pi after the number, 296 pi over 7. Or what is 296 divided by 7? It's never nice. 42.29-ish. 29 pi. Or if you then multiply that by pi, 132.84. All of those are viable answers. Again, I prefer the first one, because that one you should be able to do mostly without your calculator, and it's more exact. All right, next one. Rotate the region bounded by x equals y squared, which is a parabola going up the x-axis, and x equals 2y, which is just a straight line, around the y-axis. Okay, so since it says bounded, that means that they do intersect somewhere, so let's graph it. Again, the first thing you should always do is graph it. X equals y squared, looks like this, it's a parabola, and x equals 2y is a positive function, goes like this. So we need to find where they intersect. If I set them equal to each other, y squared equals 2y, well, that means that y is going to equal 0 when I divide y on both sides, so that gives me y equals 2 as another solution. So that gives me 0 and also 2. Now, when I graph this, whether I graph it here or if I'm not sure, I should be able to see that the curve that's furthest away from the y-axis is 2y, and the curve that's closest to the y-axis is y squared. If you're unsure and you don't have a calculator, which most times you should not, you could just plug in a value in between those bounds, for example, 1. If I plug in 1 into y in each time, I get x equals 1 squared, which equals 1. And if I plug in 1 into the second one, I get x equals 2 times 1, which is 2. That implies that the second function is the one that's furthest away, because it has a higher x number. Okay, so you can check which one is furthest away. Then we can set up our integral. In this case, we have a bounded region, so what we really have is a slice here, so something like this. And we're rotating that around the y-axis. So we're going to find that by setting up the volume as the pi times the integral. In this case, from 0 to 2 on the y-axis, of the furthest one away, which is 2y squared, minus the closest one, which is y squared, dy. That's not too bad to solve. 2y squared is 4y squared. And then when I apply my integral, I get 4 cubed y cubed. Y squared squared is y to the 4th, and then that'll give me minus 1/5 y to the 5th. These from 0 to 2. Again, like the previous case, don't need to worry about 0 because it's just going to cancel out each of them. So if I plug in 2, I get 4/3 times 8, which is 32/3, minus 32/5. Common denominator is 15 in this case, so if I do 32 times 5, that gives me 160 over 15. I believe, making sure, 2 times 5, 3, yep, okay. And then if I do 32 times 3, that gives me 96 over 15. So we get a final answer of 64 pi over 15, or whatever that is as a decimal approximation. Okay, so yeah, that's about it. Next one we have rotate the region bounded by, let's see if I can erase that, bounded by y equals x cubed, y equals 1, x equals 2, about y equals -3. Okay, so we have a lot of information there. Y equals x cubed, we know what that looks like, and y equals 1 and x equals 2 both define the first quadrant. Y equals x cubed, that's a cubic function, so something like that. Y equals 1, that's right here, so right there. And x equals 2, that would be, well, they intersect right here, that'd be 1, and then 2 would be here, so that would be x equals 2. So that's x equals 2. Whoop, bad line. This bottom one would be y equals 1. And this one right here would be x cubed. And we're rotating this around is y equals -3, so down here somewhere. So we're rotating this region all the way down past this line of -3. Okay. This one's a little bit tricky simply because we do have inner and outer radii. The one that's furthest away from the axis is from here all the way up to that curve. That would be the furthest of the slice that we're working with, the slice being this area right here, which is going along this line. That's the outer line, which is defined as not just x cubed, but it's also a distance of 3 past that. So it would actually have a distance of x cubed minus -3. You find distance by subtracting. So that means that we're actually working with an outer, so say outer, of x cubed plus 3. And we have an inner of, it was originally 0 and -3. So 0, actually not 0, sorry, it's actually 1 is my inner. My inner would be going up to here. So that would be 1 minus -3, which has a distance of 4. So that means we set up this volume as pi from, in this case, 1 to 2. That's the region I care about. The region is just this triangle right here. From 1 to 2 of x cubed plus 3 squared, that's the outer radii, or the outer radius, minus the inner radius, which is 4 squared, dx. We can evaluate that. That'll give us x to the 6th power, plus, this will give me 6x cubed, plus 9 minus 16 will actually give me -7 dx. Then we can integrate on that to give me another 1 over 7 x to the 7th. We had that before. plus that'll be 6 over 4, so 3 halves, x to the 4, minus 7x from 1 to 2. In this case, we're not as lucky as before because we don't have 0, so we do need to plug in these numbers. We have pi times, if I plug in 2 into here, 2 to the 7th is 128 over 7, plus 2 to the 4th is 16, divided by 2 is 8, times 3 is 24, minus 7 times 2, which is 14, will give me a plus 10. And then if I plug in 1 into each of these, I get, well, just the coefficients. I get 1/7 plus 3 halves minus 7. And then we can add and subtract these appropriately. First, I'll put the 1/7s together. I see that's a minus 1/7, so that's 127 over 7. That's plus 10 and a minus 7, but that's actually a plus 7, so that's 17. And then that's a minus 3 halves. And I can put that all together, although this is probably fine. We see a common denominator of 14. So if I do these, I do 127 times 2 should give me 254 divided by 14. If I make 17 divided by 14, or over 14 rather, I'd have 17 times 14 is 238, I think. Let me just check. Yep, 238 divided by 14. And then 3 halves, so I really just need to multiply the top and bottom by 7. 3 times 7 is 21 over 14. So overall, that'll give me 254 plus 238, which is 492, minus 21 is 471, pi over 14. There we go. Again, that's the most simplified it can get. Depending on your instructor, though, this might be acceptable. Just make sure you ask your instructor. Okay, so let's do a couple more examples of these. If you notice, a lot of the times looking at these, they all really boil down to setting up the equation, and then after that, it's just a lot of algebra. Okay. So here we have rotate the region bounded by y equals x, y equals 0, x equals 4, about x equals 5. Okay, well, y equals x, that's just a straight line. That's very easy. So we can graph that. X equals 5 is over in the first quadrant. X equals 4 is in the first quadrant. Y equals 0 defines first quadrant. So we have that line. That is y equals x. We have y equals 0 is the x-axis. We have x equals 4 is about, we could just say arbitrarily here. And then we're rotating around x equals 5. So 5 is here. So this is the axis that we're rotating around. Therefore, since we're doing this with washers and discs, we would take a slice like this, and we'd be rotating this around x equals 5. So that means we're going to make a donut kind of shape. Okay, so that's what we're looking for. Since I know now we're rotating around x equals 5, that means I should be using y as my primary variable in the volume integral. So v equals pi. The integration I'm bounding is from 0 to 4. Yes, it is actually still 0 to 4. So 0 up to 4 on the y-axis. It is still 0 to 4 because the line was y equals x. Let's make that a nicer 4. And then what I'm doing is I have the other two, I have my 2 radii, each squared, dy. The furthest one out, if I consider my axis, the furthest one from the axis goes to y equals x, or x equals y, I guess. However, the distance from that, the distance is defined as 5 minus minus y. That would be the distance from the axis over to the curve, or from the curve to the axis, either one. It would be 5 minus y, not y minus 5, because if I'm really trying to consider the distance, what I'm really considering is from the axis of rotation, how far away am I? So how far away is my given value? Or I guess in this case it would actually be vertically. How far away am I actually from the axis of rotation that I'm curving around? So I'm actually a distance of 5 minus y. So that should give me 5 minus y for my first radius. And my inner radius, if I do that in green, my inner radius is going to be defined as 5 minus 4, which is otherwise known as 1. So we have 1 squared. Therefore, we have this as pi of 0 to 4. Square this one out. That gives me 25 minus 10 y plus y squared. Minus 1 should actually make this a 24 dy. And then that's just a polynomial, which we can solve pretty easily at this point. 24 will give me 24y minus 5y squared plus 1/3 y cubed from 0 to 4. 0, again, into a polynomial is not going to do anything, so we really just need to concern ourselves with the number 4. If we plug in 4 into here, we get 24 times 4, which is 4 less than 100, which is 96. 4 into y squared, that gives me 16 times 5, which gives me 80. And then 4 into y cubed, 4 cubed is 64 over 3, so that's plus 64 thirds. All right, I can put all those over 3, so I can say 96 times 3 to get 288. Whoop, minus 80 times 3, which is 240. Plus 64 all over 3, which 280 minus 240 gives me just 40, plus 64 gives me 104 over 3. Hold on. No. I missed an 8. 288 minus 240 is 48, plus 64 is more than 104. It's 112 divided by 3. Yep. Okay. So that's good. Okay. Lastly, the base of a solid is the region between one arch of y equals sine of x and the x-axis. So if I draw that real quick, remember sine of x starts at 0. The first arch goes to pi and up to 1. So that is sine of x. Okay. Each cross-section perpendicular to the x-axis is an equilateral triangle sitting on the base. What we're going to do is find the volume of the solid. So what that means, if I try to graph this, because this is going to be kind of weird looking, what I'm really trying to do, let's say if I take this sign and I put it on the floor or something, and I try to make an equilateral triangle for that. So let's make this sign a little bit rotated so this looks like it's on the floor instead. And then what I'm going to try to do, each cross-section of this, I'm going to create into an equilateral triangle. So something like this. And that's going to be true no matter where I make this cross-section. So another equilateral triangle. However, that cross-section, the equilateral triangle, will depend on where I am at any given point. So that means the top of this curve looks like this. So kind of hard to see, but you're just trying to make an equilateral triangle for this curve, this sine of x. So if you make that cross-section, this creates an equilateral triangle coming out of it. And that equilateral triangle will depend on where you are in that cross-section. Okay, well, in order to solve that, what we need to do is find the area of an equilateral triangle. If you don't know the area of an equilateral triangle on the top of your head, it actually is not too bad to solve for. If we think about an equilateral triangle, let's draw a better triangle. We think about an equilateral triangle, in this case having sides of just, let's just call it A or something like that. Yeah, A, and A. Well then, we know that we can find the area of a triangle by finding 1/2 the base times the height. Well, I know the base right here is A, and I can try to find the height of the equilateral triangle, knowing that, well, since it is an equilateral triangle, this should cut it in half. So this is actually A over 2 and A over 2. That's what this altitude should do. And then to solve for this one, I can do that using the Pythagorean theorem. If I call this h, I could say h squared plus a squared over 4 equals a squared. I can subtract that over, get h squared equals a squared, actually 3a squared over 4, or 3/4 a squared. And if I square root both sides, I get the height is the square root of 3 over 2 times a, which you might remember from trig. So that means the area can be solved by 1/2 times the base, which is just 1/2 times a, times the height, which is square root of 3 over 2 times a. So that means the area can be represented as root 3 over 4 times a squared, where a is any side. All right, well, if that's the formula for the area of an equilateral triangle, and a is going to be the side length, where the side length is going to be defined by however far this curve is, then that means that I can solve for that using volume. I could say volume is equal to the bounds from 0 to pi, using the area formula of, in question, a of x dx, where in this case, from 0 to pi, the area formula is root 3 over 4 times a, which, or the distance, which is sine of x squared dx. So I'm just applying a different area formula. I said earlier that this is what we were doing was one way to find area. You could do it in a lot of different ways. So I can solve for that a little bit further. That's 0 to pi root 3 over 4, which is a constant. I can actually pull that out if I want to. Sine squared x dx. We can solve for that. I can pull out root 3 over 4. I can solve for that by using a trig identity. I know that sine squared of x as a trig identity is 1 minus cosine of 2x over 2, using one of the power rules. Or you could do like the just sine of x equals square root of this. This is 2x, not square root of x, or squared x, 2x. I can solve for that. If I have that extra 2, I can actually pull it out. Say 1 minus cosine of 2x over 2 dx. And that's solvable, because this would be root 3 over 8 times the integral of 1 minus cosine of 2x dx. That I can solve. Root 3 over 8. The inside 1 is just going to be a simple x. And then here, if you want to use u substitution on cosine of 2x, you may, by just substituting 2x as u, and then the outside would be 1/2. So you get minus 1/2 sine of 2x. And this going from 0 to pi. Okay, now to find the actual solution. Plugging in our bounds there. All right, I'll keep that root 3 over 8 outside first. If I plug in pi, I get pi minus sine of 2 pi. Sine of 2 pi is 0. Minus, if I plug in 0, I get 0. Minus sine of 0 is 0. Look at all those zeros. That makes it really, really nice. Therefore, the answer is just root 3 over 8 times pi, or root 3 pi over 8. That would be my end solution. All right, with that said, that covers everything for 6.2. At this point, you should be good to go and try your hand at the homework, which I suggest doing at this point. If you have any questions, feel free to put those in the comments below or ask your instructor directly. With that said, I hope you have a nice day.